Hello students, welcome to this revision lecture of physics for class 12. We have uploaded the regular video lectures on all the chapters of physics for class 12. Now in order to help you to answer the examination both competitive as well as in the academic examination, we are uploading some more lectures revising the chapters of physics. In the first part, we will upload electric charges and fields and electric potential and capacitance. This will help you to recollect all the formulae and theory behind the concepts of physics. I welcome you once again. Please note down all the important points. Electric charges. Electrostatics is the study of charges at rest. Charge is the property associated with matter due to which it produces and experiences electric and magnetic effect. Hence, intrinsic property of fundamental particle of matter which gives rise to electric force between objects is called charge. Conductors and insulators. Those substances which readily allow the passage of electricity through them are called conductors. Examples: metal, the earth, and those substances which offer high resistance, that is, the substances which do not allow electric current to pass through them are called insulators. Examples of insulators are plastic rod and nylon. Further, transference of electrons is the cause of frictional electricity. Charging a body can be done by friction, induction, and conduction. Properties of charges. Property number one, like charges repel and unlike charges attract. Charges are additive in nature. That means Q is equal to, it can be mathematically represented as total charge. Q is equal to summation of 1 to n Qi, where I is the number of charges. I varies between 1 to n. Quantization. Quantization, the charge exists in discrete amount rather than continuous value. Hence, it is quantized. So, therefore, it is given mathematically as the quantized Q is equal to plus or minus n into E, where n is an integer varying between 1 to n, 1, 2, 3, etc., etc. And E is the charge of an electron, and it is equal to, E is equal to, the value of E is 1.602 into 10 to the power of minus 19 coulombs. Please note it is charge is in coulombs. Charge on a body is independent of velocity of the body, and law of conservation is charge is conserved. That is, it can neither be created nor destroyed. The sensitive device which is used to identify whether the body is charged or not is called electroscope. Coulomb's law. Coulomb's law states that the electrostatic force of interaction or repulsion acting between two stationary point charges is given by the formula F is equal to 1 over 4 pi epsilon naught Q1 Q2 by R square. I will repeat, the mutual electrostatic force between 2 point charges Q1 and Q2 is proportional to the charge Q1 into Q2, that is the product Q1 into Q2, and it is inversely proportional to the square of the distance between the two charges Q1 and Q2, which is separating them. Mathematically, it is written as the force on Q2 due to Q1 is given by, and it is a vector F. Vector F is equal to F subscripts to 1 is equal to K into Q1 Q2 divided by R square into R21. in this formula, please listen carefully. F2 is the force on Q2 due to Q1, and K is the constant of proportionality. Q1 is a charge and Q2 is another charge, and R is the distance between Q1 and Q2, and R hat, R21 hat is a unique vector between charge Q2 and Q1. Here, the value of K, which is found practically, is given by K is equal to 1 over 4 pi epsilon naught. That is, the value of K is 8.988 into 10 to the power of 9, which is approximately, the value is 9 into 10 to the power of 9 newtons meter square per coulomb square. And epsilon naught is the absolute permittivity of air. This we will describe in next few lines. In ISI unit, the unit of charge is coulomb. Please remember, the unit of charge is coulomb. The constant epsilon naught, that is absolute permittivity of free space, epsilon naught is equal to 8.854 into 10 to the power of minus 12 coulomb square per Newton per meter square. Please note down very carefully and practice it. The charge is said to be 1 coulomb when it is separated from a similar charge by 1 meter, experiences a repulsive force of 9 into 10 to the power of 9 newtons. So here the value of Q1 is 1 coulomb and value of Q2 is also 1 coulomb, and the distance between Q1 and Q2 is 1 meter. If you put these values in the above formula, and the repulsive force will be F, the value of F will be equal to 9 into 10 to the power of 9 newtons. The period of revolution of the charge Q1 of mass m of about the charge Q2 along the circular path of radius is given by the formula T is equal to square root of 16 pi cube epsilon naught r cube meters m into m divided by Q1 Q2. So please click the link for detailed description of all the items mentioned in this lecture. If you plot the value of Q1 and Q2 against 1 by r square, the graph is shown in here figure. If Q1 into Q2 is negative, that is on the left side less than 0, the graph is on the second quadrant. And if Q1 and Q2, the value of Q1 and Q2 is positive, that is greater than 0, this is the plot on the right hand side. Here force is on x-axis and 1 by r square is plotted on the y-axis. Next we will take superposition principle. Superposition principle states that for an assembly of a number of charges Q1, Q2, Q3, etc., the force on any charge, say Q1, on one charge is the vector sum. Please underline vector sum of the force on Q1 due to Q2, force on Q1 due to Q3, etc., etc. For each pair of force, that is, for example, Q1 and Q2, the force is given by the Coulomb's law for two charges as stated earlier. So F total can be written as mathematically F, which is a vector, subscript total equals summation 1 to n of Fi. Here the value of I varies from 1 to n. And if expanding the formula for each combination, each pair of force, it can be written as 1 over 4 pi epsilon naught into Q1 Q2 divided by R12 whole square into R12 hat. R12 hat is a unit force in the direction 1 to 2, and R12 is the distance between 1 and 2. Similarly, for if you take the other charge Q2 as a charge, it is Q1, Q3, and the second charge here is Q3, and it is given by the formula 1 over 4 pi epsilon naught Q1, Q3 divided by R13 whole square into R13 hat, etc., etc. This is called superposition principle. Electric force and gravitational force. The ratio of force between a proton, which is positively charged, and electron, which is negatively charged, is given by the ratio Fe by Fg equals K into E square divided by G into Me divided into Mp. Here, Fe is the force, electric force, Fg is the gravitational force, K is the constant of proportionality, E is the charge of an electron which is negative, G is the gravitation constant, M subscript E is the mass of electron, Mp is the mass of proton. If you subput the values of each for in the case of a proton and electron, we get the ratio Fe to Fg as 2.4 into 10 to the power of 39. Please note down all these points. Pause the video and note down. Hitherto, we were considering two point charges. Point charges means Q1, Q2, etc. But there are cases, in practical cases, charges are concentrated over a charge distribution, length, area, or a volume. When the charge is distributed over the length of wire, it is called line charge, as shown in figure above here in a wire. So linear charge, then charges are distributed over the length of wire, and we define the unit linear charge distribution represented by the Greek word lambda is equal to delta Q by delta L. Here the lambda is the linear charge density and its unit is coulomb per meter. Coulomb per meter. So L is in meter, Q is in coulomb. So it is called linear charge distribution and linear charge density. The next, in case of a surface charge density, sigma is equal to delta Q by delta S. That is, sigma is the surface charge density. Sigma is once again Greek letter sigma, and its unit is coulomb per meter square, where delta S is the unit area as shown in figure on the right hand side. Then there is yet another volume charge distribution. If the charge is distributed uniformly on a volume, on a sphere or its object of sphere having a volume delta V, it is defined as rho is equal to delta Q by delta V, and rho is called the volume charge density and its unit is coulomb per meter cube. Hence, force due to continuous charge distribution may be written as please see the insert diagram here, insert box, vector F equal to Q naught divided by 4 pi epsilon naught into integral L, line integral L, lambda dl by r square plus surface integral sigma ds over r square plus volume integral rho dv divided by r square into r, that is r hat. R hat is the unit vector. Now, having learned about the charge, point charge, area charge, linear charge and volume charge, we will define the electric field. The electric field E at a point due to a charge configuration is the force on a small positive test charge Q placed at the point divided by the magnitude of the charge. So, it can be written as, see here, force is equal to that we can represent Force experienced by a unit positive charge is defined as the E, that is the field, is equals limit of F by Q naught. That is electric field E equals limit as Q tends to 0, force divided by Q naught. That is, it is force divided by the unit positive charge. It is a vector quantity and its unit, SI unit, is newtons per coulomb. F is coulomb. So you can remember E equals F by Q by representing a triangle. Here in the vertex is F, that is force, and in the bottom you write E and Q, where F is the force, E is the field intensity, electric field, and Q is the charge. So E, if you want to find, E is equal to F by Q, or F is equal to E into Q, or Q is equal to F by E. If you plot electric field versus 1 by R square, the graph is shown on the right hand side. So electric field due to point charge is given by K into modulus of Q divided by R square. That is substituting for the formula of F. We get electric field E is equal to modulus of 4 pi epsilon naught R square. It is radially outwards from Q. If Q is positive, that is, the electric field is radially outside, emanating from the point charge Q, and it is positive. If Q is positive, it is outwards. If the Q is negative, then the electric field is, by convention, is represented towards inwards. Electric field also satisfied the superposition principle. We had in the previous slide, in the above, not in previous slide, in this slide itself, we have above described the force superposition principle in respect of force. Similarly, we can apply the same rule for electric field intensity. So electric field E is equal to E total is equal to sigma 1 to n of EI. This is by application of superposition principle. Electric field due to continuous distribution of charges. So electric field, as in the case of superposition principle of force, E can also be defined as a continuous charge, that is 1 over 4 pi epsilon naught. Here Q is missing because we have divided it by Q. 1 over 4 pi epsilon naught, a line integral lambda dl by r square plus surface integral sigma ds over r square plus rho dv divided by r square into r hat. If we plot field intensity, electric field versus the distance, as the distance square increases, E is proportional to 1 over r square. As we increase r, the electric field decreases. Electric dipole. An electric dipole is a pair of equal and opposite charges plus q and minus q, as shown in the figure, separated by some distance 2l, which is also shown in the figure. Its a dipole moment P, vector P, has a magnitude P is equal to 2 into q into L, and is in the direction from dipole axis, that is minus q to, its direction of P is from minus q to plus q. If you want to calculate the dipole electric field at a point which is P, find a electric field at a point P which is located at a distance x from the center of the dipole, you have to apply the formula. EP is approximately is equal to 1 over 4 pi epsilon naught into 2p divided by x cube. X is shown in the figure 2 and P is located along the axial axis of AB. This is the axis of the dipole. AB is the dipole. B, this is the dipole axis. The distances are shown here, and it is assumed that x is far greater than L. L is the length of the dipole, half length of the dipole. Let it be equation 1. If you want to find out the electric field of a dipole on an equatorial plane, that is the y plane here at a point Q here in the figure 3. So if you want to find the electric field due to a dipole AB at a distance y, you have to apply the formula EQ is equal to P divided by 4 pi epsilon naught into y cube. All these things, that is y, this is y, EQ is the dipole electric field due to dipole, and P is the dipole dipole moment, and y is the distance. 4 pi epsilon naught are constant as described earlier. Let it be equation 2. So if you compare equation 1 and 2, you will get EP is equal to 2 times EQ. So please see and compare the formula for electric fields in case of a point charge and in the case of a dipole electric field. You will find that in the case of dipole, the electric field is inversely proportional to cube of r cube, that is the distance. And in the case of point charge, it is square of the distance, that is 1 by r cube for dipole, 1 by r square for point charge. As you know, there are two charges plus and minus q in the case of a dipole. Hence, the forces are equal and opposite, and the dipole does not experience any force. But there is what is called the torque, which is given by the formula torque tau is equal to P into P cross product into E. That is tau is equal to P cross E, where tau, P and E are vectors. And there are some more cases for maximum and minimum torque. The minimum torque experienced by electric dipole in an electric field, that is when theta is equal to 0 or pi, tau is equal to tau minimum equal to 0. And maximum torque, that is tau is equal to maximum when sin theta is equal to 1, that is theta is equal to pi by 2, or tau max is equal to P into E. Dipole is in equilibrium in uniform electric field when angle between P and E is 0 degrees, and in unstable equilibrium when theta is equal to 180 degrees. Net force on dipole placed in a uniform electric field is 0. Electric field lines provide the means for visualizing the direction and magnitude of electric fields. That means electric fields are imaginary lines which indicate the direction and magnitude of the electric fields. An electric lines of force is an imaginary straight or curved path along which a unit positive charge is supposed to move when free to do so in an electric field. Field lines are not physically present but represent the real life situation. Please see the diagram here. The first diagram, when the Q is positive, the direction is shown from emanating. This is a Q and the direction is outward. And here Q is less than 0, that is negative, and the direction is inward. Similarly, this is the in figure 2, it is the curved lines. So let us quickly go through the properties of flux lines. Flux lines are field lines. It is both are same. Flux lines are imaginary lines. They can never cross each other and do not form the closed loop. Electric field lines originate on positive charge and terminate on negative charge. So it starts from positive and terminates on negative. plus q and minus q in the diagram as shown in the figure. The electric field vector at any point is the tangent to the field line through that point. The electric field lines are perpendicular to the surface of the charged sphere. They are continuous curves. The density of field lines at any region is proportional to the magnitude of the electric field in that region. Here you see the density, the number of lines per unit area is more here. So it is the region of strong electric field. Whereas the distance between the electric field lines is more here, and this is a very weak field. Electric field lines do not pass through conductors but can pass through insulators. Now we will define electric flux. The total number of electric field lines passing through a given surface normally is the electric flux. So here the number of lines are passing through the perpendicular surface delta S. This shell or a semicircle, the number of lines passing through this is called the electric flux. Similarly, in this area, the uniform lines are going through. If it is passing through in parallel, it is a uniform field, and electric lines are parallel to one another, and the number of lines per unit area is the electric flux. The flux d phi of the electric field E through a small area ds is given by the relation d phi is equal to E dot ds. Here d phi, E and ds are vectors, or it can be represented as mod of E into mod of ds into cos theta. The vector elements ds is equal to ds into n hat, where ds is the magnitude of the area of the element and n hat is the normal to the area element, which can be considered planar to this sufficiently small ds. For an area element of a closed surface, n hat is taken to be the direction outward normal by the convention. Gauss law. Gauss theorem states that total outward electric flux through a closed surface is 1 over epsilon naught times the charge enclosed by the closed surface. Thus, Gauss law is the flux of electric field through any closed surface S is 1 over epsilon naught times the total charge enclosed by the surface S. This law is especially useful in determining the electric field E when the surface distribution has simple symmetry. Hence, phi E flux is represented by the letter phi subscript E is equal to charge enclosed divided by epsilon naught. This is the formula given in the box on the right hand side. Thin In the case of a thin infinitely long straight wire, E is given by E is equal to lambda by 2 pi epsilon naught r into n hat, where lambda is the linear charge density. In the case of a plane sheet of area, E is equal to sigma divided by 2 pi epsilon into n hat. In the case of spherical shell with a uniformly volume charge density rho, that is here Q is enclosed, and if you want to find the volume charge density, this is a shell. It is given by E is equal to rho divided by 4 pi epsilon naught r square into r, where capital R is the radius. Here it is shown as small r, but capital R is the radius of the sphere, and r is the distance of the charge from the outside, the point of interest. So E vector V is equal to 0 when r is less than r, that is inside the shell. Here you write capital R when small r is less than capital R, E is 0, where r is the distance of point from the center of the shell, and capital R is the radius of the shell, and Q is the total charge of the shell. Q is equal to 4 pi sigma r square. The electric field outside the shell is as though the charge is concentrated at the center. The same result is true for a solid sphere of uniform volume charge density. The field is zero at all points inside the shell. So there will be some objective type of questions. Please remember it. So here in the table on the right hand side, a comparative chart is given. So you note down the quantities, volume, surface element, electric field intensity, various dimensions, units and remarks are given. This is also given in the link in the description part of this video. Electric potential. The electric potential difference between 2 points in an electric field is defined as the amount of work done per unit positive test charge in moving the test charge from one point to another point against the force, that is electrostatic force, due to the field. Mathematically, if W is the work done in moving a small positive test charge Q from point A to point B in an electrostatic field of charge Q, then the potential difference between B and A is given by the relation VB minus VA is equal to WAB divided by Q naught. That is equal to Q over 4 pi epsilon naught into 1 over RB minus 1 over RA. Here RA and RB are distances of points A and B from the charge Q. The unit of potential difference in SI is volt. 1 volt is equal to 1 joule per coulomb. Now there is another parameter called electric potential. The electric potential at a point in an electric field is defined as the amount of work done in moving the test charge from infinity. Please underline the word infinity to that point charge against electrostatic force due to the field. So its formula is electric potential is equal to V is equal to work done WAB divided by Q naught. Q naught is the positive test charge. That is equal to 1 over 4 pi epsilon naught into Q by R. R is the distance of point A from the charge Q and its unit is volts. 1 volt is equal to 1 joule per second. Potential due to group of charges. If there are a number of charges like Q1, Q2, Q3, etc. up to Q1, whose distances are R1, R2, Rn from the test charge, then by superposition principle, V is equal to 1 over 4 pi epsilon naught into Q1 over R1p plus Q2 divided by R2p, etc. etc. to up to Qn divided by Rnp, where R1p, R2p, etc. are the position vectors. Now we will define equipotential surface. Equipotential surface is the surface at which the potential is same at all points. The points on an equipotential surface have the same electric potential. Please see the figure here. Case A on the upper side is an uniform field. That is, the field lines are parallel to one another in the direction of the field, as shown in the figure. The surface perpendicular to these lines is a plane perpendicular to this, and it has got equipotential. That means the potential in this plane is same everywhere. Here it is V1, V2 and V3. In this each plane the potential is same. Similarly, in the figure B, there is a point charge Q at the center. The field lines are emanating directly in the radial direction up to this, and the potential surface is the concentric surface. Hence, equipotential surface is surface at which the potential at all points is same. The points on equipotential potential surface have the same potential. The work done across any 2 points on equipotential surface is zero. The electric field E is always normal to the equipotential surface. The intensity of the electric field along the equipotential surface is zero. For a point charge, the concentric spheres as shown in the figure above, which are centered at the location of the charge, are equipotential surfaces. Then there is another parameter called potential energy stored in a system. So the potential energy stored in a system is the work done by the external energy in assembling the charges at their location. So potential energy stored is represented by the letter U is equal to work done W is equal to 1 over 4 pi epsilon naught Q1 Q2 divided by R1 R2. Here R12 is the distance between Q1 and Q2. Capacitance. A capacitor is a system of two conductors separated by an insulator. Its capacitance is defined by C is equal to Q by V. Here C is the capacitance, Q is the charge and V is the potential, where plus Q and minus Q are charges on the conductors with potential difference V. Capacitance is determined purely by the geometrically by the shape, size and relative positions of the two conductors. The SI unit of capacitance is farad and it is represented by the letter capital F. Therefore, 1 F is equal to 1 coulomb per volt. For a parallel plate capacitor, the capacitance is represented by the letter C naught is equal to epsilon naught A by D, where C naught is the capacitance, epsilon naught is the absolute permittivity, A is the area of the plate and D is the distance between the plates. Dielectric polarization. Dielectric develops a net dipole moment in presence of an external electric field. That is, dielectric is the material which is embedded between two plates. So dielectric develops a net dipole moment in presence of an external electric field. So dipole moment per unit volume is called polarization and is denoted by the letter capital P. The dielectric materials are mica, plastic, paper, mineral oil, etc. This dielectric material increases the capacitance by a factor K. This letter K is called the dielectric constant, which is the characteristics of the material. Hence, it is given by epsilon R is equal to K times epsilon naught. So, the value of C becomes C is equal to K times C naught. So there are two cases, capacitance in parallel and capacitance in series. Let us first take up capacitance in parallel, which as shown in the figure. Here C1, C2 and C3 are three capacitors connected in parallel. Their one end, that is the positive end, is joined together at one side and is connected to the positive side of the battery. And similarly, the negative side of the plate is joined together and connected to the negative part of the battery V. And we have also studied in our regular section the value of the equivalent capacitance is given by C1 plus C2 plus C3, etc. Here in the formula we have shown only two capacitances. Then the next case is when the capacitors are connected in series. Please see the figure on the right hand side of the screen. Here there are three capacitors C1, C2 and C3. The positive end of the plate, one capacitance C, is connected to the positive side of the battery, and negative plate of the capacitor C3 is connected to the negative end. So the negative of C1 is connected to positive of C2. Similarly, the negative of C2 is connected to positive of C3 as shown in the figure. So the equivalent capacitance is given by the relations reciprocals of the capacitance add together. That is, when the capacitors are in series, 1 over C equivalent will be equal to 1 over C1 plus 1 over C2. Simplifying, in the case of two capacitors, 1 over C equivalent will be equal to C1 plus C2 divided by C1 C2. The energy stored in a capacitance is given by U is equal to CV square by 2, that is half CV square, or Q into V divided by 2, or Q square divided by 2C. For details, you please click the link given in the description part of this video. A Van der Graaf generator consists of a large spherical conducting shell with few meters in diameter. By means of a moving belt and suitable brushes, the charge is continuously transferred to the shell and potential difference of the order of 7 million volts are generated is built up, which can be used for accelerating the charged particles. Hence, Van der Graaf generator is an equipment to increase the charge and speed of the particles. So to summarize chapter 1 and 2, here the physical quantities potential, capacitance and polarization and dielectric constant are given. The symbol of potential is capital V, capacitance is capital C, polarization is capital P and dielectric constant is small k, and its dimensions are given. The dimensions of dielectric constants are dimensionless, and unit of potential is volt, and unit of capacitance is farad, polarization is farad per meter square, and dipole moment per unit volume. Potential difference is physically significant. Now with this we have concluded, and quickly we will review the formula. Electric potential is equal to V is equal to limit of Q tending to W by Q naught, that is work done per unit test charge. Electric potential due to point charge is V is equal to 1 over 4 pi epsilon naught into R, Q by R. Relation between electric field and potential E is minus dV by dr is equal to V by R. Dipole moment is given by small vector P is equal to Q into 2L. Torque is tau is equal to vector torque is P cross E. Here it is a vector. Potential energy U is equal to minus of P into V, or Pe cos theta. Work done in rotating a dipole moment electric field in a uniform field is U2 minus U1, that is P into cos theta 1 minus cos theta 2. Electric field due to short dipole is E axis is 1 over 4 pi epsilon naught 2 pi by R cube, and at equatorial position it is E equator is equal to 1 over 4 pi epsilon naught pi P by R cube. Electric potential due to short dipole, V axial is equal to 1 over 4 pi epsilon naught P by R square, and at equatorial point potential is 0. Dielectric constant K is equal to E over epsilon over epsilon naught, that is medium, that is capacitance of the medium divided by capacitance in air. Capacitance of parallel plate capacitor is C is equal to A into epsilon naught over D. C is equal to A epsilon naught K divided by D in medium of dielectric constant in a medium, and that is equal to, if the thickness of the dielectric is to be taken, that C is equal to A epsilon naught D minus D into 1 over K. Here we are considering the thickness of the dielectric constant. So in the case of combination of capacitors, when capacitors are connected in series, 1 by C is equal to 1 over C1 plus 1 over C2 plus C3, and Q1 here charge is same. In parallel plate capacitance, C is equal to C1 plus C2 plus C3, and charge is Q1 plus Q2 plus Q3, and potential is V1 is equal to V2 plus V3. Energy stored by a capacitor is U is equal to Cv square by 2, that is equal to Q square by 2C, that is equal to Qv by 2. Electrostatic energy density is given by V E is equal to epsilon naught E square divided by 2 in air, VE into is equals E square divided by 2 in medium. Here E is equal to K times epsilon naught. Total electric flux is line integral E dot ds is equal to 1 over epsilon naught into net charge enclosed. With this, come to the conclusion of part 1 and part 2 revision, and next session we will take up chapters 3 and 4.